Okay, good morning everyone. Our topic is all about IV fabrication robustness. Next slide. Variability. We have different sources of variation, two environmental and one manufacturing. The three different sources of variation are the following: process variation, supply voltage, and operating temperature, or what we know as PVT, or process voltage and temperature. Variations are usually modeled with uniform and normal or Gaussian statistical distributions. Okay, so supply voltage. Systems are designed to operate at a nominal supply voltage, but this voltage may vary for many reasons, including tolerances of the voltage regulator, IR graphs along supply rails, and VID noise. The system designer will trade off power supply noise against resources devoted to power supply regulation and distribution. Typically, the supply is specified at 10% or nominal at each level 8. The supply varies across the sheet as well as in time. Temperature naman. The junction temperature of a transistor is the sum of the ambient temperature and the temperature rise caused by power dissipation in the package. Okay, so table 7.1 shows that the ambient temperature ranges for parts specified to commercial, industrial, and military standards. So ito yun. Minimum and the maximum. Okay. So parts must function at the bottom end of the ambient range unless they are allowed time to warm up before use. The junction temperature, or the temperature at the semiconductor junctions forming the transistors, may significantly exceed the maximum ambient temperature, and the commercial parts are verified to operate with junction temperatures up to 125 degrees Celsius. Temperature varies across the line depending on which portions dissipate the most power, and the variation is gradual. So all circuits in a given 1 mm diameter see nearly the same temperature, and temperature varies in time on a scale of milliseconds. Next step is the process variation. In the process variation, inter-die or all the transistors on one die might be shorter than normal because they were etched excessively. Inter-die, one transistor might have a different threshold voltage that is favored because of the random number of dopant atoms implanted. For devices, channel length L, channel length variations are caused by photolithography, proximity effects, deviations in the optics, and plasma edge dependencies. Threshold voltage VT. The threshold voltages vary because of different doping concentrations and annealing effects. Mobile charge in the gate oxide and discrete dopant variation caused by the small number of dopant atoms in tiny transistors. Threshold voltages gradually change as transistors wear out. Light width and spacing depend on photolithography and edge proximity effects. Metal and dielectric thickness may be influenced by polishing. Contact resistance depends on contact dimensions and edge and thickness. Process variations can be classified as follows: lat to lat or L to L, wafer to wafer, W to W, die to die, or D to D, inter-die or within wafer, or within die, WID or intra-die. Design corners. When these process variations are combined with environmental variations, we define design or process corners. The term corner refers to an imaginary box that surrounds the guaranteed performance of the circuit as shown in figure 7.5. The box is not squared because some characteristics such as oxide thickness track between these devices making it impossible to find as low and most resistors with thick oxide and fast spin transistors with thin oxide circuits. This table shows the list a number of interesting design corners. The corner is specified with 5 letters, describing the NMOS, PMOS, interconnect, power supply, and temperature respectively. The letters are F, T, and S for fast, typical, and slow. The environmental corners for 1.8 volts commercial process are shown in table 7.3, illustrating that circuits are fastest at high voltage and low temperature. Often, the corners are abbreviated to fewer letters. For example, 2 letters generally refers to NMOS and PMOS, 3 refers to NMOS, PMOS, and overall environment, 4 refers to NMOS, PMOS, voltage, and temperature.
So first, let's now go on to reliability. Reliability is designed for reliable CMOS chips, involves understanding and addressing the potential failure modes. This section addresses the reliability problems, hard errors that cause integrated circuits to fail permanently, including the following: oxide wear-out, interconnect, wear-out, over voltage, failure, latch up. Next slide, please. Reliability terminology. This is a failure deviation from the compliance with the system specifications for a given period of time. Failures are caused by faults, which are then defined as failures of subsystems. Faults have many causes, ranging from design, faults to manufacturing defects, whereas the external disturbances lead to errors. Some are masked. Next slide, please. Next slide, please. In the figure, soon after birth, systems with weak or marginal components tend to fail. This period is called infant mortality. Reliable systems then enter is called useful operating life, in which the failure rate is low. Finally, the failure rate increases at the end of life. System wears out. It is important to age systems past infant mortality before shipping products. Aging is accelerated by stressing the pipe pure burn at higher than normal voltage and temperature, as discussed in section 7.2.4. Engineers typically design product lifetimes exceeding 10 years, but it is clearly impossible to test a product for 10 years before selling it. Fortunately, most wear-out mechanisms have been observed to display an exponential relationship with voltage temperature. Thus, systems are subjected to accelerated life testing during burn-in conditions to simulate the aging process and evaluate the time to wear out. The results are extrapolated to normal operating conditions to judge the actual useful operating life. Next, the oxide wear out. As oxides are subjected to stress, they gradually wear out, causing the threshold voltage to shift and the gate leakage to increase. Eventually, the circuits fail because transistors become too slow, mismatches become too large, or leakage current become too great. Processes generally specify maximum operating voltage to ensure oxide wear-outs. Effects are limited during the lifetime of the chip. The primary mechanisms for oxide wear-out include the following: hot carriers, negative bias temperature, instability, time-dependent dielectric breakdown, or TDDB. Next slide, please. Hot carriers. As transistors switch high energy or hot carriers are occasionally injected to the gate oxide and become trapped there. Electrons have higher mobility and account for most of the hot carriers. Damage oxide changes the 1-volt characteristics of the device, reducing current NMOS transistors and increasing current PMOS transistors. Damage is minimized when substrate current I sub is large, which typically occurs when NMOS transistors see a large VDS while on. Therefore, the problem is worse for inverters and NOR gates with fast rising inputs and heavily loaded outputs, and for high power supply voltages.
Okay. Negative bias temperature instability. When an electric field is applied across a gate oxide, then green bands called drops develop at the silicon dioxide interface. The threshold voltage increases as more drops form, reducing the drive current until the circuit fails. The process is most pronounced for PMOS transistors with a strong negative bias at elevated temperature. It has become the most important oxide wear-off mechanism for many nanometer processes. When a field EOX is equal to VDD over EOX is applied for time, the threshold voltage shift can be modeled as ito yung formula for this. Time-dependent dielectric breakdown. As an electric field is applied across the gate oxide, the gate current gradually increases. This phenomenon is called time-dependent dielectric breakdown or TDDB. And the elevated gate current is called stress-induced leakage current or SILC. The exact physical mechanisms are not fully understood, but TDDB likely results from a combination of charge injection, buck-trap state generation, and track-assisted conduction. After sufficient stress, it can result in catastrophic dielectric breakdown that short-circuits the gate. Interconnect wear-out. High currents flowing through wires eventually can damage the wires. For wires carrying unidirectional or DC current, electromigration is the main failure mode. For wires carrying bidirectional or AC currents, self-heating is the primary concern. Electromigration. High current densities lead to an electron wire, means that causes metal atoms to vibrate over time. Such electromigration causes wear-out of metal interconnect through the formation of voids. Figure 7.8 shows the scanning electron micrograph of electromigration failure of a wire between M2 and M3 layers. Multiple videos taken under scanning electron microscope show void formation and migration and wire failure. The problem is especially severe for aluminum wires. It is commonly associated with an aluminum copper or aluminum silicon. Alloy is much less important for pure copper wires because of the different grain transfer properties. The electromigration properties also depend on the grain structure of the material. Self-heating. While bidirectional wires are less prone to electromigration, their current density is limited by self-heating. High currents dissipate power in the wire because the surrounding oxide or low-K dielectric is a thermal insulator. The wire temperature can become significantly greater than the underlying substrate. Hot wires exhibit greater resistance and delay. Electromigration is also highly sensitive to temperature. So, self-heating may cause temperature-induced electromigration problems in the bidirectional wire. Okay, next slide please. These causes of high peak current may even help the improvement. Self-heating is dependent on the root mean square or RMS current density. This can be measured with or calculated as heat per less. Next slide, please. This shows an example. Next slide. Soft error. Soft errors are random recurring errors triggered by the radiation striking the chip. Alpha particles emitted by the decay of the uranium or impurities in packaging materials was the dominant source of soft errors, but they have been greatly reduced by using highly purified materials. Overvoltage failure. Time transistors can be easily damaged by relatively low voltages. Overvoltage may be triggered by excessive power supply transients or by electrostatic discharge or ESD from static electricity entering the I/O pad, which can cause very large voltage and current transients. Early adoption of CMOS processes was slowed by accurate tendency of CMOS chips to develop low resistance paths between humidity and ground, causing catastrophic meltdown. The phenomenon called blast-up occurs when parasitic bipolar transistors formed by the substrate when and diffusion is turned on. With process advances and properly run procedures, blast-up problems can be avoided. Prevention. Fortunately, let's up prevention is easily accomplished by minimizing our fat and our rent. Some processes use a thick epitaxial layer of lightly doped silicon on top of a heavily doped substrate that offers a low substrate resistance. Most importantly, the designer should place the substrate and well top of the Okay, so that's the end of our presentation.
Thank you guys for listening.